Saxon Advanced Mathematics, Lesson 21. Students, today we're going to talk about functions, which are way more familiar and consistent with the work we've been doing than the word may suggest. The word sounds different and sometimes scary. It's not. Don't be afraid of these. They're fun. Before we dive into that, I want to say thank you to all of my lovely IRL students because you are doing such a great job with your check-ins. I totally appreciate how you reliably come to me every Friday and you have your work ready, your parent signatures ready, and you're on your game and you ask me questions and you tell me how you're doing, and you're doing a great job on your review problems too. So thank you very much. Those video check-ins help me more than you might realize, and they really help me feel connected to you. So thank you for bringing your A game to that work. Okay, a function has several different definitions, and that makes it confusing. One way of thinking about a function is that it is single valued. What does that even mean? It means that every time we put a certain number in, we're always going to get the same number out. So let's, for example, take, I'm going to write it in a way you're used to seeing, y equals x squared plus x, and we're going to let x equal 5. All right? So if we want to calculate y, we know that all we have to do is plug 5 into this, right? Set it up with buckets, copy it the same, plug in the 5, and we'll get 25 plus 5, or y equals 30. All right? Now, I just did that. Oh, I'm sorry. Oh, let me change it just a little bit. Minus 10. Let me just add that. I copied the problem wrong out of the book. I forgot that last minus 10. So I did it exactly the same. I just added the minus 10 to every line and then adjusted my answer, okay? My bad, I just copied wrong. But the process is still exactly the same, right? That should have a bucket around it as well. This is familiar. We're used to doing this. This is no big deal. And we know that every single time that we take this same equation and plug in the 5, we know we're always going to get 20. It's not going to change. It'll always be the same, and we'll never get anything but 20. It's single value. That's what that means. We call 5 the independent variable, because we can pick that randomly and we can change it if we want, right? It doesn't have to be 5. We could put in negative 36, but we know that we would get an answer and that answer would always be the same. That answer that is always going to be the same, that's what single valued means, is called the dependent variable, because the value of this number depends on the value of that number, right? Depending on what we put in, that drives what we'll get out. Now, you guys are used to doing this. This doesn't seem too weird or freaky. I'm throwing around some weird words we haven't done a lot before, but that's fine. That's all a function is. However, we changed the presentation just a tiny bit, and that's the first example. And I'm going to write it out for you as it's written in the book. If the f of x equals x squared plus x minus 10, that's the same as this, I forgot it before, find the f of 5. Okay, that's how we say that. If the f of x equals x squared plus x minus 10, find the f of 5. All it's saying is that this is a function and we're naming it f. For some reason, the convention is to start with f. And then if you're naming a bunch of functions, you go on g, h, I, and so on. But for some reason, we always start at f, probably because function starts with f. But all this is saying is take 5 as your independent variable, plug it in, and solve and tell us what you get. And so the process for solving it is exactly the same. I say the f of 5 equals, and I'm going to put it in buckets, because if I had a minus sign in my f value, then it might make me crazy. Okay, I plug it in just the same way I did here, except I didn't forget the minus 10 this time. And then I solve. Equals 25 plus 5 minus 10. And then we get that the f of 5 equals 20. Same as before, just a slightly different style of notation. Now, I'm going to say this once and I'll probably repeat it in the future. This highlights one really useful thing about functions. They name the equations with letters. A function is a tool that allows you to name them. Here we just called it y. What if we were solving some big hairy problem that had 10 or 20 different equations associated with it, and we wanted to be talking about them all at the same time? This tool, where we have a letter that we use to stand for an equation, allows us to talk about multiple equations without confusion. If we're just calling them y, then we're going to have a whole bunch of different equations with a y in front of them, and they may or may not be related in a system of equations. We're going to get really confused. So this is a naming tool that is super, super helpful. I always think when I'm explaining this, have you ever seen the movie called A Beautiful Mind? It stars Russell Crowe, and I believe it's rated PG. I do not think that there's anything scandalous in that movie. It's about a man who is a mathematics professor, and I don't want to say too much about it because there's some really fun spoilers. It's a movie that I love because it catches you off guard often. But Russell Crowe is the mathematics professor, and there are scenes where he's in the classroom and there's a giant big blackboard and he's got, equations scratched out all over it and all kinds of different complicated things looking on. I always think of him when I'm making this speech to you about how the letters help us keep our mathematical thoughts organized, because he paints a really beautiful picture of the kind of situation where we would want to be able to name our equations so we could talk about them. So if you're ever in the mood for a math movie, which I personally love a good math movie, I highly recommend this one. Okay, it has, it just has a fabulous big surprise in it that I find fascinating. So check it out someday. Okay, example 21.2. If the f of x equals x squared plus 1, find the f of x plus 1. Oh, this is a little trickier, isn't it? We're not substituting in just a value. We're substituting in an expression. Okay, so let's do it the same way. The f of x plus 1. We put x plus 1 wherever there was an x before. So again, buckets are the way to go, right? I just put in a bucket where my x was, and now I put an x plus 1 in there. Okay, how do we simplify that? Can we go x squared plus 1 squared? No, we have to square the binomial. So we have to do x plus 1 times x plus 1. We have to do the dance, right? So that's x squared plus x plus 1. So we're going to get x squared plus 2x plus 1 as the binomial squared. And then I'll bring this down to be another plus 1, right? So we can say the f of x plus 1 equals, let's simplify now, x squared plus 2x plus 2. Okay, so if that's an expression, we do it the exact same way, but sometimes we get a little bit of a mess going on there. After I wrote down this problem, I realized I wrote it down incorrectly, but this is the right answer for what I wrote down. So don't worry about what the problem actually says in the book. It's similar to this. It's just ever so slightly different, but I don't want to confuse you by redoing it. I did this one correctly. All right. Example 21.3. If the h of theta equals the sine of theta, find four times the square root of 3 times the h of 30 degrees. Now, when you first look at that, I bet your bones rattle, your teeth rattle, your bones shiver. You go, what in the world is this? All we're saying is that the h function is a sine function. Okay, we're not adding or multiplying or doing anything crazy to it. H is just a name we're giving to the sine function. And so all we really want to do is find the sine of this, right? So, and then we're just going to multiply it by 4/3. So we don't let this scare us. We say that the h of theta equals, oh, I'm sorry, that's writing the same thing. The h of 30 degrees equals the sine of 30 degrees. Oh, okay. And then we'll take that, whatever we get for this, and we'll multiply it by 4/3. Okay, so how do we find the sine of 30 degrees? Well, before I reach for my calculator, I think, oh, 30, 60, 90 triangle, right? That's got a 30-degree angle in it. I'm drawing that triangle. I'm imagining this one down here, but I'm not going to copy it. I'm not going to write it. I know that this is the side that stayed the same. This is the side that got chopped in half. And this is the other side, which I have memorized to that because I know it's 1, 2, and 3, but it's not just 3. It's square root of 3. And then this is the original angle. And this is the one that got chopped in half. And of course, that's the 90. Okay, so the sine of 30 degrees, sine is Oscar had. That Muppet is still choking that poor little aardvark in the alley. So opposite over hypotenuse. And this is the 30-degree angle, so I'm standing here. There I am. I'm holding my arms out to embrace the beauty of this triangle. So sine is opposite over hypotenuse. Opposite over hypotenuse is 1 over 2. So the sine of 30 degrees, which is the h of 30 degrees, is equal to 1/2. And so for my final calculation, I'm going to do 4 times the square root of 3 times 1/2. And now I know that the 4 and the 2 can cancel. And I'm allowed to do that. I'm allowed to cancel this number against this number because this is being multiplied. If we're ever adding, then we have to factor before we cancel. But this is all straight multiplication, so I'm good. That cancels. That's a 2. So my final answer is 2 square root of 3. Okay? So it doesn't always have to be complicated. Sometimes it's easy. All right, so that is our first little shot at evaluating functions. Now I want to talk a little bit more about range and domain, or domain and range is the way we usually think of them. And to do this, I'm going to talk about a sausage grinder. This is the metaphor that I was given when I was in like 2nd grade. And this whole function thing started being a thing that kids learned in school. That's a little off center, but pretend with me. Okay. The numbers that we pour into, this is our function machine. And it's sort of like a sausage grinder. okay? So what we put into it is called the independent variable. And what comes out of it is called the dependent variable, right? That describes one at a time what we put in. But the group of numbers that we choose from, that we draw from when we start putting things into the sausage machine, that's called the domain. Okay, that represents a set of numbers. So if you're making sausage, the domain represents all the different ingredients you might add. Pork, beef, chicken, different spices, salt and pepper. Those are all the different things that you would put in. You would not put in pickles, I don't think, unless you wanted sausage with pickles in it. You would not put in Cheerios. You would not put in Kool-Aid, right? I'm just trying to be ridiculous. The domain represents the set of reasonable inputs. The dependent variable is called the range, and that describes what comes out. And obviously, the range is affected by the domain, okay? And the domain is the trickier one. Okay, and the items in the range, the dependent variables, always match up to the independent variable. So if I want to make chicken sausage, then if I want chicken sausage to be what comes out, then I better put chicken in here and no salmon. Make sense? Okay, so there's our function machine. That's the handle, by the way. I don't know if you can tell. That turns the crank, that moves the gears, that grind the sausage through. All right? We'll return to that. So sometimes we have to think carefully about our domains and put some limits on our problems. So here's an example. If the f of x equals the square root of 10 minus x, find the domain of f. Okay, so we're looking at this and we're saying, is there any limit on what we can put into this function, this sausage machine here? We imagine pouring numbers in, and John doesn't state this specifically in the problems, but I should say we want this to be real numbers that comes out of this. And we know that if there's a negative inside of a square root sign, we have drama, right? We get complex numbers. So we can assume that we don't want any complex number sausages coming out of our machine. So that means that the square root of 10 minus x has to be greater than 0. Can it be equal to 0? Yes, we can handle a square root of if this was 10 minus 10, that would be fine. But we can't let x get any bigger than 10, right? Let's think about that. If x was equal to 10, then this would be 10 minus 10, and that would be the square root of 0. That would be okay. But if x was 11, 10 minus 11, that would be negative 1. That would be not okay. So that means that our value for x has to be less than or equal to 10. And another way we could find this, besides just thinking about it, is we could solve it, but I think just working it through in our heads is fine. I don't want to make this more complicated than it is. So we look at this and we think logically, x has to be greater than or equal to 0 here. The value of the value of this expression has to be greater than 0. Oh, look, I wrote the same thing twice. That's not helpful. So then we look at the x and we just think strategically, what values can my x be if I need to make sure that this value ends up being greater than 0. So this is kind of where we land on this, is that anything up through 10 is fine. What if it's a negative number? What if we have the square root of 10 minus 1? That would be the square root of 11. That would be fine, right? So as long as x is less than or equal to 0, then we should be fine. Make sense? So here's the way we write this in fancy function language. We write that the domain of f, this function that we're talking about in the first place, is defined this way. And we use these fancy symbols. We say it is, x is an element of the set of all real numbers such that, that line means such that, x is less than or equal to 10. Okay, so that's what we decided here. It's okay if x is 10, but it cannot be 11 or even 10.1, right? Anything that would make this number be less than 0, no bueno. Negative numbers are fine because we would end up adding them. So it's okay if it goes all the way down to negative a billion. We just can't let this become a negative number. So this is the fancy way that we write it, and I'll read again. This is the way we say it. The domain of x is an element of the real numbers such that x is less than or equal to 10. This is the notation I want you to pick up on. 21.5 is another variation of this. And to be honest with you, you guys, there aren't that many domain limiters. So you'll see these again and again in the problems. This is the one that tells us that the number inside of a square root must be 0 or positive. Okay, that's how I think of it. That number inside of here has to be 0 or positive unless you want a negative square root or a complex number, an imaginary number rather. And in this, we're talking about the reals, so no imaginary ones involved. This is the other one that you see again and again. We've got a function that looks like this. Do we need to limit the domain? Yes, because x minus 2 can never be equal to 0 because then the kingdom implodes and, you know, we have a bad situation on our hands. So that means if we add 2 to both sides of this, x cannot be equal to 2. That's what we know about our domain. We're going to have to restrict it. So we write out another one of these big things. I'm going to write it here. The domain of G is such that x is an element of the real numbers such that x does not equal 2. 2 is the deal breaker. Okay, so there's another version of this answer. If you understand the logic of why this one has to be less than or equal to 10 and why this one cannot be 2, then you understand the bulk of it. The rest of it is just window dressing to make it look a certain way. All right, 21.6. Find the domain and range of the function y equals the square root of x and graph the function. All right. Sorry, I was looking at the answer to the last problem and wondering how they got that for the answer to this problem. No. Okay, we know that the number inside of a square root, a pig house, can be 0 or positive, but it cannot be a negative number. So right from here, we can say that the domain has to be limited so that x is greater than or equal to 0. Does that make sense? We can do that right away. So I'm going to write it in fancy language. Domain of y is the set of all numbers where x is an element of the reals such that x is greater than or equal to 0. 0 is okay, so we put that there. And then John wants us to graph the function. Okay, so let's just make a little chart. Even though we kind of know what this looks like already. X and y. Let's choose some simple values. 0, 1, and 4. Basically, I'm choosing perfect squares so that I can take the square root of it. If x is equal to 0, then the square root of 0 is also 0. If x is equal to 1, then the square root of 1 is also 1. Finally, let's get one that's interesting. If x is equal to 4, then the square root of 4 is 2. Okay, so I'm just plugging into this equation here and mentally calculating. Let's try graphing it. And I know it's just going to be first quadrant because I know all these numbers are positive. So 0, 0, 1, 1, and 4, 2. And then we remember, you probably remember this from last year, the square root function looks like that. That should be smooth, but pretend. So now what does that tell us about the range of this function? Well, that tells us that y, these numbers, are always going to be greater than 0 as well. We're never going to get any y values down here because we're taking the square root, and the square root's always going to be positive. So we can say, in addition to this, we can say that the range of this y function equals that y is also going to be an element of the real numbers such that y is always greater than or equal to 0. All right, so when we want to graph or when we want to state the range, sometimes it's helpful to draw the function out by plotting numbers and get a sense of the way it looks, and then we can define the range as best we can from the picture. This can get a little iffy, you guys. Let's try another one like this. We haven't done a lot of graphing of some of these odd functions yet. So, but again, if you do a chart, it'll always be fine. Don't worry if this range part is a little more confusing. It's actually easier than the domain, but it feels funny at first because it's harder. You're dependent on the picture before you can say what it is. 21.7. Find the domain and range of the function y equals the square root of x plus 4 and graph the function. Okay, so we know that x plus 4 has to always be greater than or equal to 0. All right? This part in here has to be greater than 0. So let's just solve this. Algebraically, we know that x has to be greater than or equal to minus 4. That makes sense, right? Because if this is minus 4, it gets to be 0, and that's fine. But if this is minus 5, then we end up with minus 1 in here. No bueno. So let's write our domain. The domain of y equals the set of all numbers where x is an element of the reals such that x is greater than or equal to minus 4. That's correct. I didn't star these, but these were, or smiley face those are both right. Okay, now we want to plot the range so that we can take a look at what rules that's going to follow. Although it's kind of silly because it's the same shape as that, because it's a square root function, so it's going to be more or less the same. But that's all right. We'll pretend we don't know. So we make a chart. I'm going to do it the way I prefer to make the charts, which is where I write the function in here. I didn't do it on this one, but I prefer to do it so you can see where I got the y values. So let's choose our values carefully. Let's start with negative 4. So when I plug negative 4 into this, I get the square root of negative 4 plus 4, which equals 0. The square root of 0 is 0. All right, let's choose 0. So then I have the square root of 0 plus 4, which is the square root of 4, which is positive 2. I can write that there. Oh, this is, okay. All right, and then the other one, let's try 5. And once I do it, you'll understand why. The square root of 5 plus 4 equals the square root of 9, and that is 3. I like it. So now I'm going to graph, and this time I know I'm going to need some negative x values, so I'm going to go ahead and draw 2 quadrants instead of just 1. And I'm going to put a few marks on here. These do not have to be perfect, you guys. Understanding is more important than a graph you slaved over, although make sure it's neat enough that you understand what you're doing and anyone else could understand what you're doing, but you don't have to slave over the details. Notice I don't put the numbers in. I just put enough hash marks in so that it looks reasonable. Don't let yourself get sidetracked at this point by trying to beautify your graph. Now I'm going to plot these points. -4, 0, 0, 2, and 5, 1, 2, 3, 4. I need one more. 1, 2, 3. So look, I still have a square root curve, but it's going like that. And I can say the same thing I said last time, which will always be true of these functions, and that is that our y value is always going to be positive. And I see it here in the chart, right? It starts here and it's only going that way. So I can say that the range of function y equals the set of numbers where x is an element of the real, where y, because I'm talking about domain. So I'm talking about these values. Y is an element of the reals such that y is always greater than or equal to 0. And that's the second part of my answer. Again, it's easier to find the ranges if you can look at the picture and just see, okay, what's happening with my y. One more of these problems, and I want you to see it, but I don't want you to get confused by it. So if this one makes you a little crazy, but you understood all of those, you're fine. Example 21.8. Find the domain and range of the function f of x equals the square root of x divided by x minus 2. Okay, this one is double drama because we've got to keep this positive and we've got to keep this away from 0. So I know that x has to be greater than or equal to 0, but x can also not be equal to 2. Do you see how I've got an x in 2 places, so I have to have 2 different rules? So to write the domain, that's pretty easy. The domain of f is the set of all numbers where x is an element of the reals such that x is greater than or equal to 0, but also x is not 2. Double checking. Bum, bada, bum. Yeah, you can just put a comma in between them. That's fine. All right? That's our domain. Now, this is where it's hard. In order to find the range, we want to draw this graph and take a look at what the y's are doing. But we haven't done a graph this complicated in ever, I don't think. It's much more complicated than the ones we did in the previous examples. So let me show you what the graph looks like, and then we'll decipher what the range, what that graph is telling us about what the range must be. The graph of this function looks like this. It goes down, then, right, because x has to be greater than 0, but those are negative numbers. And then we have a dotted line here at 2 because we said that x cannot be equal to 2. So here's x being greater than 0. Here is x not being equal to 2. And then here's a wacky curve like that. What in the world do we do with that, right? Well, we just look at the y's. We don't have to worry about what's going on with the x's. We've already come up with that limitation on the x's. Let's just look at what's happening with y. And what we see is that y starts at 0. It includes everything negative. And then this arrow, this asymptote, tells us that this number is going to keep getting smaller until it approaches 0. way out in infinity land, right? So what that tells us is that y is really going to cover all of the numbers, negative and positive and 0. So the answer is quite simple. I'll write it here so you can see it. The range of f equals the set of all numbers where y is an element of the real numbers. And there's no limits on it. It can be positive or negative. It can be 0. The only way we could tell that was by looking at this graph, and this graph is way more complicated than we have learned to graph so far. So I call dirty pool on John. I don't think that's a fair question, and it's this style of function that makes us crazy. Okay? So if you understood everything else, but you don't get how John came up with that graph, don't worry about it. You're fine. Okay? We're going to get to things like this later, but for now, that's out of our pay grade. So don't worry about it. All right. The next section I'm going to teach mostly out of the book because there's lots of pictures and it moves quickly. Another thing we know about functions is that a proper function creates what we call a mapping between the domain and the range. For every element in the domain, it should be mapped or related to one image in the range. It maps to that. That's the word that we use. So when we put 4 into this function, we get 3. When we put 2 into the function, we also get 3. But every time we do 4, we get 3. Every time we do 2, we get 3. That is a proper function. Here's another really nice function. It's called a one-to-one function. This one wasn't a one-to-one function. In this one, every number it maps to a different value in the range. There's no sharing. So this is a function, but this is a special kind of one-to-one function. We don't make that distinction a lot. And we see more of this kind, but this is a function too. It's okay if the guys in the domain share a range partner, but what's not okay is something like this. In this situation, this number 4 maps sometimes to 3 and sometimes to 5. That's a problem for a function. That doesn't work because remember we said our functions are single valued way back in the beginning of this lesson, which you might not remember anymore because it was about 50 years ago. But this scenario is a problem. This is not a function because 4 does not go to the same number every time. The 2 going to 6, that's fine. But this situation with the 4, no bueno. We call this a relation though because everybody in the domain does have a partner over here, as opposed to this one where 4 to 3, that's fine. 2 to 5, that's fine. But look at 1. He's just chilling. He doesn't have a partner. He does not map to anyone in the range. He's not even a relation. He's just no good at all, right? So if we can build relationships between the numbers like this, then we can decide whether or not we have a function or a relation or nothing at all. Sometimes John will show a function by showing us a list of pairs. And then what we have to do is we have to kind of visually translate it to this presentation. The first number is in the domain, the second number is in the range. So we look and see what's happening. 4 to 3, that looks good. 5 to 7, that looks good. 9 to 3, okay, fine. Now we hear 4 again. Now we already had a 4 and it mapped to 3, but here we're saying the 4 maps to -5. Ooh, that's not a function then. It's a relation because everybody's got a partner, but 4 cannot make up its mind. So that's a relation and not a function. What about this one? Here we have 4 goes to 3 twice. This one's fine, right? Because every time that you have 4 in the domain, you end up with 4 in the range. So that's cool. All right, so that is a function. And then John's going to test us on these, and we'll just use his pictures. I hope you could see those other ones. I might have been blocking the light a little. All right, 4 goes to 3, 3 goes to 3. That's cool, that's a function. It's not a one-to-one function, but that's fine. It's a function. A is a function, yes. B, all right, 7 goes to 3, that's good. 5, 5 is a 2-timer. Sometimes 5 goes to 4, sometimes 5 goes to 3. No bueno, you're not a function. You are a relation, but you're not a function, so get out of town. C, oh boy, C's got real problems. 4, 6, check and check, but look at M. M has no one and nothing. So that is neither a function nor a relation. That's just a problem. Now, this one's tricky because it's presented completely differently, but let's try and make sense of it. X is an element of the real numbers, so that's what we are using for our domain, all real numbers. The function is given to us as a statement, y equals x plus 2. So the range is going to be whatever we chose for our x's plus 2. That all makes sense, doesn't it? So that is a proper function because even though we don't have specific examples, we know that any number we choose over here, we can run through this function and our answer will look like that, right? Because we're just going to add 2 to anything. So D represents a function as well, but that is a very new way of looking at it. So keep that in mind. Oh, we're almost done, you guys. Just a few more points. Here is a problem using that other formatting. So which of the following sets of ordered pairs are functions? So what we're looking for is that if we see the same number in the domain position, the first part, then it has to be the same number in the second part. Right now I'm just looking at the first number in each pair. 1, 2, 3, 4. Everybody's got a partner. We're good. A works. B, I'm looking at just the first numbers, 1, 2, 1. Okay, I've got a repeat now of my x values, my my independent variables. So now I better check and make sure it's connecting with the same thing. Dang it, it's not. Here 1 relates to 2, here 1 relates to 3. Sorry, you don't work for me. You might be a relation, but you are not a function. And that's what the question asks. So B fails. Oh, excuse me. Time out for a yawn. I yawn when I talk a lot. So imagine. C, okay, let's look at just the independent variables, just the domain values. 4, 2, 4, 3. Okay, we have a repeat, but look, 4 is partnered with 3 both times, so it maps as a function. Yay. So we said yes, no, yes, and I'm just checking. Yes, no, yes, and now D, I'm looking at just the first values, 1, 4, minus 1, 3. That appears to be fine. Everybody's got a partner. There are no repeats, so we don't run the risk of anybody being a 2-timer, which honestly is how I think of this. These relations, this 5 is a 2-timer, right? Sometimes he dates 5 and sometimes he dates 4. No, get out. You're not a function. All right? So the problems can take either style. The last part of this are 2 tests that we can use to determine if something is a function. The vertical line test is beautiful. We take a shape, let me just show you in the book. Let's say we have a function and it's been graphed and it looks like this. We're going to get to these later in the year. They're fun. How do we know if that's a function or not? There's a very simple test. The vertical line test tells us simply draw some vertical lines, verticals up and down, right? I always have to stop and think about that. And look and see how many times each one of those lines crosses the original function. Okay, so I'm going to put dots there. This is where the red line is crossing the green curvy line. Does the red line cross the green curvy line more than once? No. Okay? And I can't imagine any way that if I drew another line, I could get it. So a vertical line test, if it's a function, it will intersect the function. The vertical line will intersect the function at no more than 1 point? Yes. For some functions, it would be possible to draw a vertical line that doesn't cross at all. That's okay, that's not the problem. But our vertical line cannot cross at more than 1 point. Okay, and so let's do an example of that one next door so you see what I'm talking about. Here's our graph. Here is our shape, and we're trying to determine if this is a function. I want to use a different color. So look what happens with this vertical line test. Uh-oh, right? It's crossing twice. So this is a fail. And this is a win over here. Okay, and it all just can be determined by the crossing those vertical lines. Now, there's a second test. I'm going to do it on the other page. So vertical line tells us if it's a function or not. But there's a second test that will tell us if it's a one-to-one function, right? And we draw those like so. I'm choosing different colors. All right, this is, okay. If I had drawn this precisely, it would pass the vertical line test. These are a little bit too straight in my picture. Let me draw it again and try to make it a little bit more. There, you can see it better in that one. So let's just cross that off. Okay, remember in your homework, you don't have to erase things. You don't have to scribble them out hard. Just make it clear, no, I don't mean this, right? Just like I did. All right, in this one, if we try to draw another line, I'll use orange for my lines this time. This is the, did I say orange? I meant brown. The horizontal line test. In the horizontal line test, we draw the lines this way. It's already passed as a function, but with the horizontal line test, if this intersects the line at no more than one place, that means it's a one-to-one function. So this one is a win because our lines are only crossing at one place. And now let's do a fail. I'll draw it up here so this corner doesn't feel. A nice parabola, a little wiggly there. But this one is not a one-to-one function because look, if we go this way, it's fine if we go this way, right? It passes the test to be a function, but here we're getting multiple hits. So this fails the horizontal test. It is not a one-to-one function. This one passes because it hits, the horizontal lines hit only once. So that means it's a one-to-one function. This, I don't like the way I worded it, so let me go back and make sure I'm clear. This vertical line test is when we draw the vertical lines and they intersect the shape. That's a better word. If it intersects the shape at no more than one point, then the shape is a function. I think I said it right, but I don't like the way my words tried to explain that. And then the same thing here. Here I said line. I don't like that either. If it intersects the shape at no more than one place, then the shape is a one-to-one function. All right? So those are fun little tests that you can easily apply to test whether your shape is a function and then whether it's a one-to-one function. All right. And if you look, last problem is one with pictures, so let's just go through it. Determine if it's a function, and if so, determine if it's a one-to-one function. Okay, so A, we start with the vertical test, and we see that's going to get multiple hits, isn't it? So that one's not a function. Done. B, yeah, we can draw lines on that all day, and I don't think it's going to hit more than once, so it's a function. Now let's try going horizontal. That looks fine too, so it looks like B is a one-to-one function. Yep, it is a one-to-one. Okay, what about this one? Ooh, this is kind of confusing. Can you see how there's a solid dot and a circle dot? Okay, so if I draw vertical lines, I think I'm gonna hit just once on each one of those, right? The trickiest one is right here where there's a solid dot, but then directly below it is an open dot. So that means I only hit at the top. So this one looks like a function. However, when I go to test it with the horizontal line for a one-to-one function, no, it fails miserably, right? It's gonna have a bunch of hits there. So it's not the graph of a one-to-one function. And this graph is the graph of a function, okay? So yes, function, no one-on-one. And then we try this one. Vertical test, look, it fails right there because we have two dots over and above each other. Doesn't pass the vertical line test. So that is how that goes. And now we're done with lesson 21. That was really long, you guys, and it was not necessarily complicated calculations, but it was a lot of messing with your mind. So let me know if you are confused by any of that. I mean, I'm sure you're somewhat confused because who wouldn't be? But when you get ready to sit down and do the problems, let me know if you can figure them out or if that's what's going on in your brain. All right, next time we have some fairly straightforward calculations and it's a little bit less burly a lesson. So I'll see you at lesson 22.